In an earlier video we showed how two H2 and one O2 molecule can rearrange to form two H2O molecules. Because a new substance is formed, this change qualifies as a chemical reaction. We'll now replay the reaction in slow motion to show 3 snapshots in time as the reaction goes through different stages. At the beginning, there are two H2 molecules and one O2 molecule. These starting substances are called the reactants. When the molecules bust apart into atoms, there are 4 hydrogen and 2 oxygen atoms, and at the end there are 2 H2O molecules. These are called the products of the reaction. We can see how the bonds change during the reaction by using structural formulas showing the symbols joined by sticks. When the reactants bust apart, 2 bonds within the H2 molecules and a double bond within the O2 molecule are broken. When the products are assembled, 4 new bonds are made inside the H2O molecules. Scientists have a shorthand way of writing these changes called a chemical equation, which uses an arrow to show the molecules before and after the reaction. The reactants are written on the left of the arrow and the products on the right. In this case, the reactant molecules H2 and O2 are written on the left, and the product molecules H2O are written on the right. Scientists don't usually bother with the in-between stage of busted apart atoms because this doesn't last very long. O and the AND in the equation is replaced by a plus sign because it's quicker and it means the same thing. Notice that there are 2 H2 molecules at the beginning. We could show this by putting an extra H2 on the left of the arrow, but it's quicker to write a 2 in front of the H2 to show that there are 2 of them. It means the same thing. The same applies to the H2O molecules on the right-hand side of the equation. The easiest way of showing that there are 2 of them is to write a 2 in front of the molecule. Numbers in front of molecules are called coefficients. They count the number of molecules taking part in the reaction. Let's count the number of molecules before and after the reaction. At the beginning there are 2 H2 and 1 O2 molecules, 3 altogether. After the reaction is complete, there are only 2 H2O molecules. That looks like a bad deal. We've lost a molecule during the reaction. That's true, but let's look at atoms instead. Before, we had 3 molecules each made of 2 atoms. That's 6 atoms altogether. After, we have 2 molecules each made of 3 atoms. That's also 6 atoms altogether. The number of atoms has remained the same. That makes sense, because we can't lose or gain atoms just because they change partners. When a quantity stays the same during a change, we say that it has been conserved. Here, the number of atoms has been conserved. We can take it even further. Not only have the total number of atoms been conserved, but the number of atoms of each kind has also been conserved. Let's look at hydrogen atoms before and after the reaction. We started with 2 H2 molecules, that's 4 hydrogen atoms. We ended up with 2 H2O molecules. With 2 hydrogen atoms in each, they also contain 4 hydrogen atoms. No change. Let's look at the oxygen atoms. At the beginning there's 1 O2 molecule, and this contains 2 oxygen atoms. At the end there's 2 H2O molecules, which also contain 2 oxygen atoms. No change. Because the atoms don't change their weights, this is also called the law of conservation of mass. That's just a fancy way of saying that there's no loss or gain of mass during a chemical reaction. And we can use the conservation of mass law to help us write chemical equations so that the atoms add up, even if we can't see the movie of the molecules where we can count them. In this case, we know that the reactants are hydrogen gas and oxygen gas, and that the products are water molecules. Let's get rid of the movie and see if we can work it out just from the words in the equation. From our bonding rules, we know that hydrogen's formula is H2, oxygen's formula is O2, and water's formula is H2O. A quick glance shows that the number of hydrogen atoms on both sides of the equation is equal. An H2 molecule contains 2 hydrogen atoms, and so does one H2O molecule. But if instead we look at oxygen, we can see that the left-hand side has 2 oxygen atoms inside the O2 molecule, but the right-hand side has only 1 inside the H2O molecule. They're not equal. We can't fix it by changing water's formula to H2O2 because it would no longer be water. But we can double the number of H2O molecules on the right-hand side by putting a 2 in front of the H2O. Because 2 H2O molecules contain 2 oxygen atoms, both sides of the equation have the same number of oxygens. Oops! By doubling the number of H2O molecules on the right-hand side, we have also doubled the number of hydrogen atoms to 4. 2 water molecules, with each one containing 2 hydrogen atoms, means 4 hydrogen atoms in total, 2 multiplied by 2. But we still have only 2 hydrogen atoms in the H2 molecule on the left-hand side. By balancing the oxygen atoms, we have frustratingly unbalanced the hydrogen atoms. No sweat. We can change the number in front of the H2 molecule to 2, which means that there are 4 hydrogen atoms on the left-hand side also. There are now the same number of atoms of each kind on both sides of the equation. 4 hydrogen atoms and 2 oxygen atoms. We call this a balanced chemical equation. We've figured out how to balance the equation for H2 and O2 reacting, but we can also apply these same principles to balancing other chemical equations. We'll do that in the next video. Then you can try a few on your own.